What is the density of propane at 77 degrees and atmospheric pressure? So we know the temperature and the pressure, and we're dealing with propane. What we're going to do here is apply the ideal gas law. So this is another really common topic and theme that comes up again and again. Sometimes we're not always able to assume that the ideal gas law applies, but in this case we will, because we don't have much other information or any reason to believe that we would have another approach here. So this is definitely going to be the way to go. We know the pressure and we know the temperature. We don't know the volume, but there's a clever trick that we can use. We can actually deal instead with the density or the specific volume. So how do we do that? Well, we could divide both sides by volume, and then on the left side it cancels out, and on the right side we end up with m over v. Well, what is m over v? That's mass per unit volume, or pounds per cubic feet. That is density. So then we can rewrite the expression as P equals rho RT, which is a nice simplification. And then that's extremely helpful because what we're looking for is the density. So now we can rearrange this and say density equals pressure over RT. And we know the pressure and the temperature, and the R is the gas constant, and you can use the universal gas constant and then divide by the molar mass for propane, or an easier way is to just directly look up the specific gas constant for propane, the R value, and we can do that by looking at properties of ideal gases. There's a table in the reference handbook called Properties of Ideal Gases. And in there we can go and look up propane, and it turns out that R for propane is 35.04 foot-pound force per pound mass Rankine. So that's pretty much everything we need in order to find the density. We just have to do a little bit of unit conversion. So it said we have atmospheric pressure, so that's 14.7 psi. And instead of writing it as psi, I'm actually going to write it as pound force per inch squared, which is what psi is. But I just want to do that because that will help remind us that since we're going to have feet in the denominator, we want to end up with feet cubed, cancel out. So we have to get rid of inches. And you'll see this all work out in just a moment. So we'll put 144 inches squared, or you can do 12 inches over 1 foot and square the whole fraction, but I think this is pretty clear either way. So that's going to get rid of our inches squared, and now we have the numerator, the pressure, in PSF, pounds per square foot. The denominator is our RT, so 35.04 foot-pound force per pound mass Rankine. And then the temperature, which needs to be in Rankine degrees. So instead of 77F, we got to add 460 to that. 77 plus 460, and then that will have units of Rankine. So Rankine will cancel, pound force will cancel, and this feet will come up into the denominator of the numerator, if you will, and become feet cubed. And then this pound mass will come up into the numerator, and we're going to end up with units of pound mass per cubic foot, which is exactly what we want for density. And the magnitude of that value is 0.11 pound mass per cubic foot. Best answer choice is C. Would you like to have more solution videos like this one so you can pass the PE exam? Click the link in the description below to take your next step toward becoming a licensed professional engineer.